Okay, hi everybody. I have the hiccups, so I might hiccup. Maybe this will cure me doing a video. Anyway, definition of log as an inverse function. And then we're going to derive an integral formula for log. I mean, we're literally going to derive it, like differentiate, and that's how we're going to get it. But anyway, so first of all, why are we doing this? Remember the story. So we didn't actually get a definition of e to the x in the book, so I'm telling a little bit of a different story than our book. If we start with arguably the simplest differential equation, that we have some unknown function f, and we're just going to say, hey, what if that function were a power series? Wouldn't that be nice? And then we found out that if it was, well, it would have to be this power series. All the coefficients are 1 over n factorial. And so this infinite series is now a function. It takes in an x, and it spits out the limit of the sequence of partial sums of this thing. Okay? And if we force an initial condition, namely that at time 0, at time x equals 0, we force it to be 1, that actually played a role in these a sub n's. Otherwise, we would have a constant out here. But yeah, now that constant is 1. And so that's how we get our x. And we give this a name. We call it exp. Or we could call it f. Or we could call it, and actually what we do is we proved that it has a nice property that justifies the name e to the x. Why is that a good name? Well, because we found out that this is true. And this matches what would be true for, 2 squared plus 2 to the 5th. 2 to the 5th is 2 squared times 2 to the 3rd, right? That is sort of power rules. I don't know what you call this, exponent rules, something like that. So we have this function, and we can compute it. In fact, we checked. This is absolutely convergent. By the ratio test, the limits of these consecutive ratios of the terms was actually 0. It was completely independent of what x you chose. That is awesome, because that means that you can choose any x at all in the complex numbers, and the limit will be less than 1. We can compare to a convergent geometric series. Do you remember the proof of the ratio test? Go back and watch that video if you don't. And that shows that actually this is a great function, and we can compute it for any complex number and definitely any real number. Then we were like, hey, complex numbers, there's like this whole imaginary axis that has I on it. It has twice I on it, and 3 times I. It has theta times I on it. So for every theta in the real numbers, let's compute e to the I theta. We saw that these are always on the unit circle. That's amazing. And we also saw that they move at unit speed around that unit circle, and that they start there. That's e to the 0 being 1 is right there. And so this actually gave us right away from this wonderful function that we can compute, it gave us the geometry of sine of x and cosine of x being, the y coordinate and the x coordinate of a unit circle point. And then we just pull out, if we plug in, where is it? We plug in e to the I theta, we get actually the i's, we get like things like this. Sum, infinite sum, and the even powers of I will become 1 or minus 1. The odd powers of I will become I or minus I. And so the imaginary component will be those odd powers. And they're just going to oscillate between I and minus I and minus I, and we just pull out the I to get the imaginary component. And then the real component, where you had an even power of I, that was just going to be 1 or minus 1, 1 or minus 1. And so we get this. I guess this is a minus. Anyway, Now we can actually compute these things. We couldn't compute these before. We had the geometry of them. We could literally draw a circle and try to measure these. But now we can compute them very precisely. We can compute this very precisely. There's really just one more thing that we can't do. How do we do that? Does anybody know what the log of 3 is? You might object and say, oh, we have Taylor series. Taylor series. That's sort of something like the nth derivative evaluated at a point A, and then we do this, and then we do this. And the problem is, though, when n equals 0, you need to be able to evaluate your function at A. Then you can take the derivative times x minus A. Then you can take the second derivative evaluated at A times x minus A squared over 2 factorial plus da 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 da. And you could get really good approximations using this, but you have to know f of A. So we apply this to log, like let's say log of 3. We need to know log of 3, and then we can start computing, well, okay, what's the derivative of log? Well, that's a good question. What is the derivative of log? Turns out it'll be easy. What's the second derivative of log? It'll be easy. So all these are going to be okay in the Taylor series, but we need to get started. Okay, so now I have sufficiently completely ignored the question and just talked for a really long time. So now let's actually do the question. So let's get rid of this stuff. Explain the definition of log as an inverse function. So we have a nice computable function that sends x to e to the x. Okay? Computable, I mean like you can approximate it to any desired accuracy because it's absolutely convergent. And it'll take any complex number at all, but we're gonna, for this problem, just let it eat real numbers, and it's going to take and spit out positive real numbers. Then the inverse function will be named, well, we're just going to create a name for it. We're going to create the name log, or ln. I just like writing log. And what is it? What does log do? Well, log takes a positive real number and spits out a real number, right? It goes from the outputs back to the inputs. It undoes this function. So it has to start here and go there. Okay. Now great, this is helpful. We have no idea how to compute this. Pretty much because we know e to the 0 is 1, then we know that the log of 1 is 0. So good, we can compute what this does to the number 1. It sends it to 0. But, we still don't know what does it do to the number 3. Derive an integral formula for log. Okay, we have to use our derivative of the inverse function. So let's call g and f a function and its inverse. And we know that g of f of x has to be x again. So let's apply d dx to this. What does that give? It gives g prime evaluated at f of x times the derivative of the inside function, which is f prime at x. That is the chain rule. The right-hand side, derivative of x, that's 1. But then g prime of f of x is equal to 1 divided by f prime of x. By the way, here's our f. Do we know the derivative? Yeah, it's the easiest one ever. It was defined to satisfy the easiest differential equation. I don't know, easy, but simplest. Okay. And now what's f of x? Well, f of x we're calling y, and then g of y we're calling x. So g prime of y, f prime evaluated at, well, x, but x is g of y. So now, replacing, what do we get? We get that the derivative with respect to y of log of y, that's this side, equals 1 over the derivative of the exponential function is just the exponential function again. So f prime became exp. And what's g? G is log of y. But hello, these are inverse functions. These are inverse. Wow. The derivative of log is just 1 over y. And look at this. We know how to compute this. Okay? And so to me, like if I was on a desert island and a magical monster, it was going to eat me, and the only reason that they wouldn't eat me is if I could tell them the logarithm of 3. What I would do is I'd say, well, I know the derivative of log is 1 over y. So why don't I integrate from 1 over y somewhere to somewhere, and I want to get a function out of this. And so I'll say that the log of x is equal to, well, why don't I start somewhere and end at x, and this will be my variable. So the variable is well, here's 1 over y, the graph, and I need to start somewhere, and then my variable is how far I go, and the number, log of x, will be this area under the graph. If I go farther, I get a bigger number. So you see that this depends on how far I integrate. If I go farther over here, then I get a different number, so it depends on how far I integrate. Now, what do I want? I want that log of 1 equals 0, because e to the 0 is 1. And so to make that happen, if I plug in a 1 up here, I want 0, so why don't I put a 1 down there? Then the integral goes nowhere, and I get 0, okay, for log of 1. So then my function, I'll just have be start at 1, go to x, that'll be log of x, and this is our answer. So if somebody asked me for log of 3, this monster, then I would just, I can compute this function. At 1, it's 1. At 3, it's 1/3. And I can split this up. At 2, it's 1/2. I can split this up and start doing Riemann sums super easily. So my first approximation would be this area, which is 1 times 1/2. My second approximation would be this area, which is 1 times 1/3. So my approximation to log of 3 would be this. Now that's not going to be very good. It's going to be too low. And so I could chop it into smaller pieces and get a little bigger of 4 rectangles and add up those 4 rectangles. They'd be different values, but you see I'd be able to do this. To whatever accuracy the monster desired, I could just split this up into smaller and smaller pieces. Derive an integral formula for log. The derivation is all of this. Okay, can you do this? Blank sheet of paper, without looking. Try it out.